Hello there and welcome again to our continued series of mathematics lessons. We are still looking at this topic on length, area, surface area and volume. In our past lessons, we have been able to cover length up to and including perimeter and circumferences of circles. We have been able to cover area. We have also been able to cover the surface area. Today, we are going to make an introduction on how we can be able to calculate the volumes of prisms and also volumes of cylinders in our next lesson. I'd like to make a review of what we learned on length and surface area. We said that the distance connecting 2 points, let's say A and B, the distance between A and B is the one that we refer to as the length. And whenever we have a closed figure, let's say A, B, C, D, and you need to find the total length around this particular figure, then that will end up giving you the perimeter. And we said perimeter is distance around a figure as this. We were also able to cover perimeter on a circle, which we are calling the circumference. And when you are given a circle of a given radius r, we can be able to find the distance around this particular circle, and that will end up giving us the circumference of that particular figure, which will be equivalent to 2 pi r, or if we are using the diameter, then that will be pi d, where pi is the fixed constant 22/7 or 3.142, and then d is the diameter of that particular circle. In the case we have a circle that is not complete, this is a circle that is not complete and it is a quarter of a circle. Given that this is the radius, it will be equivalent to that of the other side. We can be able to take this angle 90 degrees to be theta. Then for us to be able to find the perimeter or the distance around this particular figure, then you must take into account these two radiuses plus the distance from this point to this other point, which shall be given by the angle divided by the total angles, which is 360 multiplied by 2 pi r. So in the case we are given that this is 90 degrees and we are given a radius of 7 degrees, 7 units for instance, then the perimeter of this particular figure can be found by making those particular necessary replacements in our formula. So this shall be 2 multiplied by the radius, which is 7, plus the angle subtended at the center is 90 degrees, and that is our theta, divided by 360 degrees. We multiply this by 2, we multiply by pi, which is 22/7, and we multiply by the radius, which is 7. This will give us 14 units, plus this one cancels, there ones, here 4, 2 there 2, 2 there ones, 2 there ones, 2 there 11. So that shall be 11, and therefore the total distance around this particular figure shall be 25 units. We were also able to cover areas. And we are able to look at areas of different solids or different figures. We began by looking at areas of triangles, and in this case is when you are given the base and the height of that particular triangle, and we say that area in this case will be given by a half multiplied by the base multiplied by the height of that particular triangle. So given that we have a right angle triangle with a base of 4 units and a height of 5 units, we can be able to calculate its area by using the formula a half multiplied by the base, which is 4, multiplied by the height, which is 5. So this one will give us 2 multiplied by 5, which will be 10 square units. We're also able to look at areas of quadrilaterals, where we say that a quadrilateral is any 4-sided figure, or a figure that has got 4 sides. And there are so many. We have got the square, we have the rectangle, we have the trapezia, parallelogram, the rhombus, and so forth. A square, its area can be obtained by taking the square of its length. Area is equals to length squared. If you have a rectangle normally has 2 opposite sides being equal and parallel. We can be able to refer to the longer side as the length and the shorter side as the width, and therefore its area is normally given by length multiplied by the width. We can also have a parallelogram, for which we said that the area of a parallelogram will be given by the base multiplied by the height of that particular parallelogram. We also have a trapezium, and we say that for a trapezium, area will be given by a half multiplied by the addition or the sum of the 2 sides, that is the longer side and the shorter side, all these multiplied by the height h. We are also able to look at how we can be able to find the area of a rhombus. Where we say that a rhombus is a twisted square, and for you to be able to get the area of a rhombus, which is a twisted square, we normally take a half multiplied by the product of the diagonals. So given that this is our rhombus, that these 2 are our diagonals, this is x and this is y. So when you take a half of the product of the diagonals, you get the area of a rhombus. Again, on areas, we are able to look at how we can be able to get areas of composite shapes. And for composite shapes, we say that these are shapes that consist of more than 2 or more different shapes. So that, for example, when you're given a figure as this, we can be able to say that this is not one shape. There are 2 shapes. We have got this semicircle here, and we have this other one that wanted to form a rectangle. So if you're asked to find the area of such a particular figure, which is a composite shape, given, let's say this is 6 meters, the longer side is 10 meters, then for us to be able to find the area of this composite shape, we need first to get the area of the whole figure before subtracting a half of a circle, and therefore area will be given by the area of the whole triangle will be length times width, which will be 10 multiplied by 6, and that will be meters squared. We subtract this part here that is not included, which is in the shape of a half a circle, which will be given by a half pi. Given that the diameter is 6, the radius will be 3 centimeters multiplied by 3 squared. So this will give us 60 meters squared. We subtract a half pi multiplied by 3 cubed, which is 9. Which will give us 14.1429 square meters. So when subtracted from 60, you'll get that the area of this figure is 45 and 6/7 meters square. So this kind of a figure, we refer to it as a composite shape. Composite because it is made up of more than one shape. And this is a case where we are subtracting. There are other cases where instead of subtracting those areas of those other parts that are making up that particular figure, we do add. Another part of area that we're able to look at is how we can be able to find the area of a circle. And in that particular case, we're able to say that area of a circle is normally given by pi r squared, where pi is constant and r is the radius of that particular circle. So that if you are given a circle which has a radius of 14 meters, for example, then you can be able to obtain the area of this circle by using that particular formula, where pi is 22/7. The radius is 14 squared. So 7 will go into 14 twice, giving us 22 multiplied by 14, which will give us 308. The units are in meters, so we have square meters. The last aspect that we covered on areas was on unit conversion. And on unit conversion, we say that the basic conversion or unit conversions are the ones normally convert from kilometer square to meter square to centimeter square and also to millimeter square. We discovered that when you want to move from kilometer square to meter square, then this forward arrow, we take 10, we multiply that by the square of 1,000. The square of 1,000 in this case will be 1 million. The same from square meter to centimeter square, we again multiply by another 100 squared, and again from square centimeters to square millimeters, we multiply by a square of 10. Notice that when you'll be going back from square millimeter to centimeter to square centimeters, we do the reverse. That is, we divide by 10 raised to 2. From square centimeters to millimeter to meter square, we do the reverse. We divide by square of 100. And again, from square meters to square kilometers, we again divide by the opposite of that, which is 1,000 square. we notice that when we talk about 1000 squared is the same as 1 million. When you talk about 100 squared is 100 times 100, which will be 10,000. And when you talk about 10 squared, this is 10 multiplied by 10, which shall give us 100. The last aspect, which we also covered in our last lesson, was on the surface area. And we say that surface areas are normally applicable for solids. These are figures which are in 3 dimensions, or they have got more than one surface. And there are very many, ranging from the cubes, the cuboids, and also on prisms and pyramids. I like to talk about one of them, which is a prism. And in this case, we talk of a prism which has a square base of 4 units by 4 units. By now, you should be able to understand that a pyramid is a figure that has got an apex, or the edges are meeting at one particular point. So we say that the most important thing whenever you want to calculate surface area of solids, then we need to know how to deduce the net of that particular solid. So let's assume, or let's take our height of one of those triangles to be 5 units. So we need to reduce this solid into a net, where we shall be talking about the same solid but in 2 dimensions. So we shall have the base, which you have said is 4 by 4. Then we have got 4 triangles, each on every side of our figure. Now, for us to be able to calculate the area of this solid, which is a square-based pyramid, then you need to take the area of the base, then we add the areas of these 4 triangles. So in that case, area or total surface area shall be given by length squared plus, the triangles are 4, and each triangle can be obtained by taking a half multiplied by the base multiplied by the height. Our length is 4 units, so that is 4 squared plus 4 into a half multiplied by 4 multiplied by 5. So this will give us 16 square units plus 2 there once, 2 there twice. That will be 10. 10 by 4 is 40. So this will give us 56 square units. So in a nutshell, that is what we were able to learn during our previous lessons. So I want to look at how we can be able to calculate or find volume of prisms. At this juncture, it should be understood that whenever we are talking about volume, we are talking about the number of cubic units that are contained or that are occupied within a 3D figure or solid. So volume is the number of cubic units occupied or simply contained within a 3-dimensional solid or object. Another important aspect on the volume is on conversion from one unit of volume to the other unit of volume. The most common units of volume is kilometer cube, meter cube, centimeter cube, and also millimeter cube. Same with what we are doing on conversion of areas, the same can be done on volumes. Now from cubic kilometers to cubic meters, we are supposed to multiply this one by the cube of 1000. From cubic meters to cubic centimeters, we are supposed to multiply the units here by the square of 100. And again, from cubic centimeters to cubic millimeters, we are supposed to multiply this one by, this one is cubed, by the cube of 10 or 10 cubed. Then when you are going back or during the reverse processes occur. From millimeter cubed to centimeter cube, we reverse this action. That means we divide it by the cube of 10. From centimeter cube to meter cubic, we do the reverse of this, which is dividing it by the cube of 100. And again, from cubic meter to cubic kilometer, we are supposed to divide this by 1000 cubed. And again, it should be understood that whenever we are mentioning about 1000 cubed, 1000 cubed is the same as 1000 times 1000 times 1000, which will give us 1 billion. 100 cubed is the same as having 100 multiplied by 100 multiplied by 100, which will give us 1 million. And then 10 cubed is the same as 10 multiplied by 10 multiplied by 10, which is equivalent to 1000. Another important aspect is on capacity. Whenever we mention capacity, we talk of the contents of that particular container. How much of liquid or how much of a substance can that container be able to contain or to absorb? And in this case, in capacity, we talk, in most cases, talk in it about the liters, milliliters, centiliters, and so forth. But the most important units which are going to use when dealing with capacity is the megaliters, which is denoted by capital M, capital L. We have the kiloliter, denoted by KL. We have another unit of capacity, which is liter, denoted by L. We have another, or the smallest, which is the milliliter, and is normally denoted by small letter m, capital L. Those are the 4 units of capacity whenever we want to talk about the volume of a certain container in terms of its contents, or what can be put inside that particular container. Again, just to mention, on conversion from one unit to the other, the most important is converting from megaliter to kiloliter, from kiloliter to liters, and also from liters to milliliter. In this aspect, if you have 1 megaliter, it's equivalent to 1000 kiloliters. And again, 1 kiloliter is equivalent to 1000 liters. Similarly, 1 liter is equivalent to 1000 milliliter. So from one to the other, you either multiply or divide by 1000, depending on which one you are going to and where you are coming from. But you have said the greatest unit of measurement for capacity is the megaliter. Now, whenever you are given a solid that has a uniform cross-section area, like for example, we have this is a cuboid. Now, with this cuboid, there is a surface which we can be able to say that is the cross-section of this particular figure. Cross-section in the sense that if you were to cut alongside that particular edge anywhere within the figure, then we are going to obtain 2 similar solids. So in this case, you find that you can be able to cut out this solid at this particular point on that plane surface, and you'll obtain 2 solids that are equal in terms of volume. Therefore, that particular plane that has been cut off, which relates also to this other side, then is the one referred to as the cross-sectional area. Then this other side will be the length of our solid. Now, for you to be able to get the volume of a solid which has a uniform cross-section, or the uniform cross-sectional area, then you take the area of that cross-sectional area and you multiply by either if it's the length or the width of that particular, the length or the height of that particular solid. In this particular case, let's talk about it in terms of being the height. Therefore, volume is equals to cross-sectional area multiplied by the height or the length of that particular figure. Common formulas. For volume. Number 1, when you have a cube or a cuboid that has this side labeled the length, the other side labeled the breadth, B, and has a height, H, then for you to get the volume, you take the length, you multiply by the breadth, and also multiply it by the height, which can be simplified into LBH. B, if we have a prism which has a rectangular, not rectangular, but triangular cross-sectional area, where you are given that this is our height of that particular triangle, and this is the breadth of that triangle, and this is the second height, or H2. Then for us to be able to find the volume of this particular figure, then we take the cross-sectional area, we multiply by its height. And given that the cross-sectional area in this case is in terms of a triangle, then that shall be given by a half multiplied by base multiplied by the first h1 or height 1, then we multiply by the second height, which is the length, which is h2. So in this case, this can be shortened as that, a half bh multiplied by h2. But in most cases, this h is the length of that particular solid in question. We want to consider a number of examples on how we can be able to find volume and also convert from one unit to the other. Convert the following volume measurements. Into units given in brackets. Number 1, we have 2.5 cubic meters, which is supposed to be converted to cubic centimeters. We had originally said that for you to convert from cubic meter to cubic centimeter, then you multiply by a cube of 100. That means that 1 cubic meter is equivalent to 1 million centimeters cube. So when we are talking about 2.5 square meters, we can be able to do a cross multiplication of this, and this will give us 2.5 meters cubed divided by 1 meter cubed multiplied by 100 cubed, and this shall result or will give us 2,500,000 cubic centimeters. That is because 1 meter cube is equivalent to 1 million cubic centimeters. So if you have 2.5, then you simply multiply that 2.5 by a cube of 100. Part B, we have 458. This is millimeter cubed and is supposed to be converted to centimeters cube. So again, we recall from the introduction, we say that for you to convert from millimeter cube to centimeter cube, that means you are going back, and therefore you need to divide through by the cube of 10. Or in simple terms, we had said that 1 cubic centimeter is equivalent to 10 cubed millimeter. Therefore, if we have 458 millimeter cube, for us to be able to get to convert it to cubic centimeter, we do a cross multiplication, and this will give us 458 millimeter cube divided by 10 cubed is 1 million millimeter cubed multiplied by 1 cubic centimeter. So this will give us 0.458 cubic centimeters. Another example, find the volume of each of the following. Part A, we have 3 cuboids which have been put one top of the other. So those are 3 cubes which is measuring 1 centimeter by 1 centimeter. Each of these is 1 centimeter, so in total we have 3 centimeters. Now we'd say that for us to be able to get the volume of such a figure, then if you are given the length, the breadth, and the height, then its volume is given by L, BH, where L is the length, B is the breadth, and H is the height. And now in this case, our length is 1 centimeter, our breadth is 1 centimeter, and our height is 3 centimeters. So this will give us 3 cubic centimeters. Part B of the question. We have a figure that has got a uniform cross-sectional area. And this cross-sectional area, we have been told, is equivalent to 10 square centimeters. And the height of this object is 5 centimeters. You see, for this particular piece of object, it has what we call the cross-sectional area, in the sense that there is a part. If we are to cut along this piece, along this edge or this side, then we are going to have an equally similar surface to this surface that is here on top, and therefore that forms its cross-sectional area. And for us to be able to get the volume of this object, which has a uniform cross-sectional area, then we said you take the cross-sectional area, you multiply by the height. We have been given that the area of this cross-sectional area, which has already been predetermined, is 10 square centimeters. So we multiply by the height, which is 5 centimeters. This will give us a total of 50 cubic centimeters, which is now the volume of this particular solid or object. The third one, we have a figure that has taken the cross-sectional to be in form of a triangle. And we are told that this side is 6 centimeters. The whole of this is 4 centimeters, and that the height here we have been given to be 3 centimeters. If you are able to observe this particular figure keenly, then you will discover that in this particular shape, there is one surface. If we were to cut along, then it will be equivalent to this particular section, and this is no other than this particular part. So that tells us that this triangular surface is the cross-sectional area of our solid, and therefore for us to be able to find the volume of this figure, then we need to get the area of the cross-sectional area, and we multiply by the length, which in this case is 6 units. Because we have a triangular cross-sectional surface, then the area will be given by a half multiplied by the base, which is 4, multiplied by the height, which is 3. Then the whole of it is multiplied by the length of that figure, which is 6 units. This will give us 6 multiplied by 6, which will give us 36 cubic centimeters. Because this was in centimeters, this is in centimeters, also this is in centimeters, it shall result to 36 cubic centimeters. Example 3, a brick is 10 centimeters wide, 20 centimeters long, and 8 centimeters high. How much space would 5 of such bricks occupy? So during the introduction, we said that volume is the number of cubic units that are occupied by a 3-dimensional figure. A brick is a 3-dimensional figure. Let's take this to be our brick. It's in the form of a cuboid. We have been told that it is 10 centimeters wide, it is 20 centimeters long, and it is 8 centimeters high. And then we've been asked to calculate how much space will be occupied by 5 such bricks. That means you must first get the volume occupied by one brick, then because there are 5 and all of them are equal, then we multiply by 5. So volume of one brick, we had said, will be given by length multiplied by the breadth multiplied by the height. In this case, our length is 20, our breadth is 20, this was 10. Our breadth is 10, and our height is 8 units. So when you multiply, and this will be cubic centimeters. So 20 by 10, that's 200. 200 multiplied by 8 is 1,600 cubic centimeters. Now this is the volume that is contained, or the space occupied by a single brick, that is 1,600 cubic centimeters. So in the case that we have 5 of them and they are similar, that means in terms of the shape and also the dimensions, then we simply multiply the result here by 5. So space occupied by 5 will be 1,600 cubic centimeters multiplied by 5, which will give us 8,000 cubic centimeters. So this is the space, or the total space, that will be occupied when we have 5 bricks combined together, or 5 bricks of dimensions 20 by 10 by 8. Example 4, how much airspace is contained inside a rectangular cardboard box that has the dimensions 85 centimeters by 62 centimeters by 36 centimeters. Answer using cubic meters, correct to 2 decimal places. So we have been asked to find the volume of the air that will be trapped inside this cardboard box, which is rectangular in shape and has a dimensions of 85 by 62 by 36, which gives us, or tells us, that this particular cardboard box is a cuboid. So if this is our box, we have been told the dimensions are 85 centimeters by 62 centimeters by 36 centimeters. We are supposed to obtain or calculate the volume of this particular object. Then after calculation of this particular, and our answers should be in cubic centimeters, in cubic meters, and correct to 2 decimal places. There are 2 ways of working out this particular problem or question. The first one, because we are interested with the units of volume being in meters cube, then we can be able to convert all these units of length into meters first, or we straight away calculate the volume using these units the way they are, then convert back to cubic meters using the units of conversions we had seen earlier on. So the first part, alternative A, is to convert these units of measurement into meters. So this one into meters will be 0.85 meters, 0.85 meters. This one will be 0.62 meters. This one will be 0.36 meters. This is because 1 meter is equivalent to 100 centimeters. And given that volume is normally given by the length times the breadth multiplied by the height, then this shall be 0.85 meters multiplied by 0.62 meters multiplied by 0.36 meters. This will give us 0.85 multiplied by 0.62 multiplied by 0.36 will give us 0.18972 cubic meters. We have been asked to write to 2 decimal places, so we count 1, 2, we consider the third figure. So this shall be equivalent to 0.19 cubic meter. Alternative B will be to work out using this centimeters as it is. So volume will be given by length times the breadth multiplied by the height, which in this case shall be 85 centimeters multiplied by 62 centimeters multiplied by 36 centimeters, which will give us 189,720 cubic centimeters. And we had said that whenever you want to convert back from cubic centimeters to centimeters, then we need to divide this by 100 cubic units. So this shall be equivalent to 189,720 divided by 100 cubed, which is the same as 1 million. Which will still give us 0.18972 meter cube. And then because the question wants us to round it off to the nearest 2 decimal place, this again shall be 0.19 cubic meters. We would like to consider the last example on volume of prisms. Example 5, where we are told that 25 liters, now this is capacity, 25 liters of water is poured into a rectangular fish pond, into a rectangular fish tank, into a rectangular fish tank, which is 50 centimeter long and 20 centimeter wide, and 20 centimeter high. The question is, will it overflow? Now, for us to be able to answer this question, we need to know what capacity does this rectangular fish tank hold in terms of water. And we talked of how we can be able to convert from units of volume to capacity units. Now, volume that this rectangular fish tank holds will be given by the length multiplied by the breadth multiplied by the height, which is 50 by 20 by 20. and all of these are in centimeters units. So this will give us 50 by 400 shall give us 20,000 centimeters cubed. Now we have been told that 25 liters of water has been poured inside that particular box. We need to know, is this volume accommodative of this amount of water that has been poured? Then that means we need to convert this from cubic centimeters to liters. And we had said that 1,000 cubic centimeters is equivalent to 1 liter of water. Therefore, if we have 20,000 cubic centimeter space, then that means this particular rectangular fish tank can be able to accommodate or hold water up to 20,000 divided by 1,000 liters, which shall give us 20 liters. So the box can be able to hold 20 liters, and we are pouring in water which is 25 liters. The question was, will it overflow? And the answer is yes. There will be an overflow because the capacity of the tank is 20 liters and we are pouring in 25 liters. So that means that the amount of overflow will be 25 less 20, which has been accommodated inside the tank, which shall be 5 liters. Now this brings us to the end of the discussion on how we can be able to calculate volume of prisms. In our next lesson, we shall be able to cover how we can be able to find volume and also capacity of cylinders. Thank you.